Hello everyone. Today I'll be presenting our project on content-based image retrieval (CVR) across different image sizes and formats. This project is about solving a very practical problem where images are stored in different file formats and or resized. They are often treated as completely different even though they are visually the same. So our team wanted to build a system that can recognize these similarities so that searching and managing the images becomes easier. Here comes the challenge of the image recognition. Imagine you have a huge digital library of photos and will upload images as PNGs, JPGs, and sometimes the other file formats. And they are also resized for different uses. And to the human eye, all these versions are clearly the same photo. But for a computer, a small resize or a format change can totally throw it off. So this causes problems in real life. For example, copyright protection, where deleting duplicates is crucial, or in companies that store millions of images and want to avoid duplicates taking up the space. So that's why our goal is to build a content-based system that retrieves visually similar images regardless of resolution or file format. Let's see the case snippet where an image named ice cream.png, and I've also stored ice cream underscore small dot jpg. For the visual contents, both of those are similar, um, but a normal system won't recognize them as the same. So hence our goal was to fix this with content-based features. And coming to the existing approaches, over the years, researchers have developed multiple ways to retrieve images, which are deep learning, texture and edge descriptors, and color histograms. The evolution of CBIRs reveals these techniques. And for the deep learning, neural networks like CNNs work very well, but they need huge data sets, long training times, and lots of computational resources. And for the texture and edge descriptors, these focus on the structure of images, edges, shapes, and textures. They are lightweight, but not always reliable if the background is too complex. And for the color histograms, these summarize the distribution of colors in an image. They're easy to calculate, robust to rotation, and small translations and efficient. Uh, each of these approaches has trade-offs. So we wanted to test one that's computationally simple but effective. So we have chosen color histograms, specifically normalized histograms, because they give us two key benefits: computational efficiency and robustness. Normalization helps us compare images even if they are of different sizes, because we are comparing proportions instead of raw counts. Yes, they do have drawbacks. They ignore spatial details. For example, a red ball on a white background and a red car on a white background might look similar just because the color mix is similar. But for our project scope, this method gave us a good balance between complexity and practicality. For the methodology, we designed a workflow of 5 main steps. The first one is the dataset, where we started with 10 images and then manually resized and reformatted them to create variants such as JPG, PNG, and more. This let us test if our system could handle differences in size and format. And the second one is color quantization. We reduced each image to a 6-bit RGB representation using a MATLAB function. Instead of 256 colors per channel, we shrink it to just 64 possible colors in total. This reduces the complexity. Histogram generation. For each image, we built a 64-bin histogram using getHistCounts.m. Then we normalized the histogram so it could be compared across different sizes. For the database construction, all the histograms were stored in the database using build database. This became our searchable index. And the retrieval, we used run demo to process queries. We compared the query histogram to those in the database using the Euclidean distance. The smaller the distance, the more similar the images. The pipeline is simple, but it makes sure that if you resize or change format, the essential color distribution still allows the retrieval. Here comes the good case. So on the left is the query image, which is a cat, and on the right you can see the retrieval output. The system brought back all the resized and reformatted versions of the same cat image. Notice the distances are really small, close to zero, which means the system saw them as highly similar. In terms of matrices, we got a precision at phi of 1.0 and an F1 score of 1.0, basically the perfect. This shows that when the task is just recognizing the same image under different formats or sizes, the histogram method works very well. And a bad case, the query image is the red rows, and the system should ideally return similar flowers or the related content. But if you look at the retrieval output, instead of flowers, it matched images of cats. Just because they had some strong red tones in them. This happened because color histograms only look at the distribution of colors, not what the objects actually are. So, as long as there are a lot of red, the system assumes they are similar, even though to us they are clearly very different. So, that's why the precision here drops to 0 and F1 score also drops to 0. And this example really highlights the main limitation of using only color features. The system gets confused when two unrelated images share similar color distributions. And the reflections, first, even simple methods like color histograms are powerful of handling size and format variations. Second, their biggest limitation is ignoring spatial relationships and object structure. In the future, we could extend this by combining multiple features, color plus texture, descriptors like filters or edge-based descriptors. Another direction would be to add deep learning to capture semantic information. That way, the system won't just say this is red heavy, but it can also say this is a red car, not just a red thing. So here's the demonstration of the system working. Now I'll walk you through the live demo of our CVIR system in MATLAB. So we implemented some key functions for quantization, histograms, creating the database, and for retrieval and display. For the color quantization, the first normally an RGB image has 256 possible values per channel. That's 16 million colors in total. So we reduced that to a 6-bit code, meaning 2 bits per channel. That gives us only 64 distinct colors. So this makes the system much simpler while still capturing the essential color information. So for the build database. This function scans through all images in the data import folder, whether they are PNG, JPG, or BMP or JPEG, and process them. For each image, it converts it to the 6-bit color space, calculates a 64-bit histogram using getHistCount.m, and then stores that in db.map. So basically, the db.map file is our searchable index. It contains all the image histograms plus their file names. So when the database is saved, MATLAB prints how many images were processed and confirms that the matrix is ready. And for the query processing, we have used the run demo function. So when I'll type the command like run demo image o1.png, then the code does few things automatically. It loads the database, process the query image the same way as before, and builds a histogram, and then computes the Euclidean distances between the query and every database image. So the distance acts as a similarity measure, and the smaller the distance, the more similar the histograms are. This is how we calculated our distance here. So basically, I'll show you an example command for the cat auto image. As you can see, the results are displayed in this figure window. At the top left, you'll see the query image, and then the system shows the top 5 retrieved matches ranked by similarity. Each result has a heading showing its rank, such as match 1, match 2, match 3, and etc. And the Euclidean distance code too. And so if the system is working correctly, resized or reformatted versions of the query image should appear among the top results as it does now. So yes, this works well across the format and sizes for the cat02.png, and this is our best case actually. And for the worst case, sorry, my bad. This is our query image, which is a red rose. You can see that the top results, and you can also find the limitation because the image has the dominant color, which is red, and the system may sometimes return visually different images with similar color distributions. This highlights one of the weakness of our system. And so in summary, the demo shows how our pipeline works end to end for the quantization, histogram generation, database, indexing, and retrieval. It performs very well when images differ only in size or format, but it struggles in cases where color similarity doesn't represent actual content. So that's why we suggested some future improvements like adding texture and deep learning features.